Estupendo.
To continue, we have to Diego Souza introduce to Professor Francisco Gancedo. You can start there.
Okay, thank you, Juan. So for me, it's a great honor to introduce Professor Francisco Gancedo, well known as Paco. Paco received his PhD in 2007 under supervision of Professor Diego Córdoba at the Universidad Autónoma de Madrid. Paco has more than 40 publications and more than 1,200 citations. And also, thanks to his contribution, he was awarded with many national prizes like José Rubio de Francia, Antonio Valle, Manuel Lozada Prize, and he received many. His research has been supported by many agencies, national agencies, and also he led an ERC grant. And his main research topic is the analysis of PDEs with origin in fluid mechanics. And today, Paco is going to talk about global in time dynamics for one-phase Muskat and two-phase Stokes gravity waves. So Paco, welcome, and thank you very much for accepting the invitation. So you can start.
Okay, thank you all for the invitation. It's a pleasure for me to be here. Thank you, Diego, for a very nice introduction. So please stop me at any time. I'm not very familiar. I just gave a few lecture online. So let's see how this goes. So I'm gonna talk about one-phase Muskat, two-phase Stoke wave. So the thing that we are gonna have in common among the cases I'm going to consider is just we are gonna have gravity force, okay, moving our fluids, okay. So the first thing I want to talk about is a joint work with Hong Ji-Don at Brown, Hui Kwang and Guyen at Maryland. And the second part of the talk is going to be a joint work with Rafa Granero at the University of Cantabria and Elena Salguero at the University of Seville. Okay, so I'm going to talk about fluids. We had already a very nice talk about waves, the classical wave equation. As you see in this nice picture, we have like water wave over here. But today I'm not going to talk about water wave. I'm going to talk about the wave that you see over here in sun. Okay, so this line over here is the wave that you see when we have a moist region, when we have fluid over here, and a dry region, okay, in porous media. So let's think in fluid a filter in porous media, or you think in sun, okay? And I want to understand the kind of wave that you see over here, okay? Very good. So let me show you the equation. From the fluid mechanics point of view, the equation I'm going to consider are very classical, okay? So what we have is an incompressible fluid, okay? U is going to be the velocity of the fluid, and we have the incompressibility condition. So let's think in water, if you wish. Rho is going to be the density of the fluid. So what we have over here is the conservation of mass, okay? And then the equation we're going to use to model the evolution of the fluid is the classical law to model the evolution of a fluid in a porous media, which is Darcy's law, okay? If I want to summarize a lot, Darcy's law essentially tells us that because a fluid is inside a porous media, the forces, we have pressure and gravity. Okay, we are going to move. Well, let's to get rid of some constant and make things more clear. Let's living a planet with gravity equal to 1. This is not going to be important for our talk. So our forces given by the fluid due to the pressure and gravity are proportional or equal to momentum. Okay, here mu is the viscosity of the fluid. Okay, and this is just the momentum. Instead of acceleration, instead of forces equal to acceleration, we have forces equal to momentum because our fluid is inside a fluid. Okay, very good. So what is the Muskat problem? The Muskat problem is when we consider two different fluids. Okay, so in the domain D1, we have a fluid with viscosity mu1 and density rho1, and in a complementary domain, let's pick 2D, right? So you see the picture that I show you, okay, is exactly what you have to have in mind, right? Here we have, if you wish, a domain D1, which is moving with the fluid. Here you have another domain D2, which is moving to the fluid. And then what we want to understand is the dynamic of these free bonding, okay? And in D1, we have a fluid with density mu1 and rho1, and in D2, which is the complementary domain, we have another fluid with viscosity mu2 and rho2, okay? Very nice. So let me show you the interface equation very quickly, how to get it, in the case I'm interested, in which in D1, we have viscosity and density equal to 0. Okay? In this case, is the picture that I showed you, in which, because viscosity is 0 and density is equal to 0, we have a dry region. So we have a dry region and a fluid region. Okay? So if I remember you the equation, remember that we have incompressibility, and then Darcy's law inside the fluid. Okay? So if we look at Darcy's law, okay, this is a constant value because a fluid has a constant viscosity. Then it is very easy to check that just because of Darcy's law, the constitutive law, our velocity is rotation, right? Because it's given by two gradients, right? So because it is irrotational, we can write the velocity through a potential, okay, gradient of P. So this allows us to integrate Darcy's law. Okay, we can integrate. Remember that our variables are x, y. Okay, so we can integrate. Very good. So this is not difficult, right? We can integrate. So what we are gonna do is to describe our set, let's say D2, okay, given by a graph. Okay, simple case, given a graph. So we have this thing over here given by x, f, x, t, right? Because it's moving with the velocity of the fluid. Okay. So because our velocity is a potential and is divergent free, is a potential, it is very easy to see that our potential is an harmonic function, right? Laplacian of P is equal to 0 in D2. We want physical relevant cases, so this gradient of the potential is just the velocity. So what we are assuming here is just that we have finite energy because we are assuming that our velocity is in L2, okay? And then, going here to Darcy's law, I give you how is the potential at the free boundary. Okay, let's remove T for some just to simplify a little bit. So at the point Fx, pressure is 0, okay, because this is the condition. I'm not going to consider self-extension. If we do not consider self-extension, our pressure is continuous on the surface. So because we have here, let's say, a dry region means that the gradient of the pressure is equal to 0, and then our pressure has to be continuous. So the pressure is 0 on the surface, and what we get is just the gravity condition. If we pass viscosity to the other side, what we get is exactly this condition for the potential, okay? So what we have is that a solution of the potential in terms of the interface, okay? Very good. So what give us and close our equation? The dynamic condition, right? How is evolving the free interface through the normal velocity, okay? So the tangential direction is not moving particle, okay? So what is moving the velocity? So the tangential direction is not moving particle, okay? So what is moving the interface is the normal direction of the velocity, right? So this is how our interface is moving. So what we have is the normal velocity of the potential is what is giving us the dynamic. So what we have over here is a Dirichlet to Newman map operator. Okay, this is the Dirichlet to Newman map operator, right? Because we are giving a Dirichlet condition. Okay, we have a Dirichlet condition, and to see our dynamics, we need the normal derivative. So this is the Newman condition. Okay. So what I'm with this notation, G F is going to be the profile, which is this profile over here, and F is going to be the value that we give on the boundary. Okay. Very good. Please ask me anything. I'm not sure. You can maybe open your microphone and you have questions. Okay, so what I'm gonna do in the next slide, which can be maybe a little bit fast, is what I'm gonna do is just show you the equation, just using the double-layered potential theory. Okay, so if you believe the last equation that I showed you, the evolution is given by the Dirichlet to Newman map. Okay. And then if we use double-layer potential theory, we end up to this equation over here. Okay. Okay, so we know the kernel in R2 for the Laplacian, and then using the double-layer potential, we get this non-local and implicit equation, which is kind of a mess. Let's do the simple case. Let's say periodic. They have a periodic interface that repeats all the time. So I have a period, okay, and then I repeat it. So that's the reason why in the kernel that I'm writing here, you see the hyperbolic sign, okay, over here, hyperbolic sign, and this is the hyperbolic cosine, okay. Okay, so if we analyze this, what I want to show you is to analyze this a little bit. Okay, analyze to linearize and to have a more clear idea. This is the no local, no linear equation I have to handle, which is a big mess. But let's try to simplify this a little bit. So if we expand a little bit, the thing that we see here downstairs, if we expand this thing, the cosine to the Taylor expansion and the hyperbolic cosine to the Taylor expansion, what we see is that downstairs we have a kernel x prime of order 2. And if we expand the kernel that we find here on top, what we have is a kernel which is of order 1, x minus x prime squared. This is just, no square, sorry. This is just Taylor expansion, okay? So in total, I have a kernel of order -1, right? Very good. If I do the same thing in the equation for theta, which is my potential, in the double layer potential theory, what you see over here is that over here, I have a minus sign. I Taylor expand this thing, and then what I get on top is order 2 also, right? Because of the Taylor expansion. This is if you reply sign by x minus s prime and hyperbolic sign by exactly the thing, what we have over here is what we need to cancel the Taylor expansion, okay, for order 1, and then at the end we get order 2. And then downstairs you have order 2, x minus x prime order 2. So at the end of the day, we have order 0. So this is telling us this is order 0. We are integrating here. Okay, so at the end, this is telling us that theta is at the level of g. Okay, and remember that here g, sorry, at the level of 1 derivative of g, and g here in my equation is f. So at the end, what we have over here is a kernel of order -1 applied to 1 derivative of f. Okay, let me simplify this with the linearization. I just wanted to show you this calculation. If this is not so clear, this is the simplification. Okay, what you see over here, oh, sorry. What you see over here is a kernel of order -1, as I told you, with the tangent applied to 1 derivative. Okay, this is exactly, if you go to harmonic analysis, this is exactly the Hilbert transform applied to 1 derivative, sometimes called the Finum operator or the lambda operator. Lambda is just the square root of the Laplace. Okay, so if we go to the Fourier side, it's very easy to get the solution of the system that I showed you. Okay, so in the Fourier side for node, okay, so what we have is given by this exponential. So this is like the heat equation, okay, for this quantity positive, okay, but instead of the Laplacian with the square root of the Laplace, okay. Very good. So remember that I told you the case in which we have the fluid here. We have here the fluid on top, and this corresponds to the stable case. Okay, this is the stable case when we have the fluid below. Then what you see over here, when this one constitutes positive, what we have is the fluid below, and then this is a good equation, right? The heat equation with the square root of the Laplace. Okay, but if on the other case the fluid is on top, what we get is an unstable situation. Okay, this corresponds to the case in which this is negative. Okay, and then this is a disaster equation. Okay, so even for very regular or C infinity initial function, this doesn't make any sense. Okay, so we have here two regimes, very important regime, which is the stable case or the stable regime and unstable. Okay. Very good, depending on where the fluid is. Okay. So I'm gonna talk about the stable case. In the unstable situation, this system is imposed, and then wild thing can happen. So I would like to talk about the stable situation. Okay, so this thing that I described is the Muskat problem, which is a classical problem from 1934. Also considered in a very classical setting by Safman and Taylor. It's turned out that in a Hilly-Shaw cell, which is this draw over here, in which you can put like two fluids inside a Hilly-Shaw cell. Hilly-Shaw cell essentially consider two plates close enough together, and then you put a fluid inside. okay, and then essentially the fluid move into direction, okay. Okay, so mathematically, if you go to the equation, this situation can be these two different physical situations mathematically are analogous, okay. Very good. So here you have some classical results, okay. So what I want to show you in the next slide are recent results. You see results from the last year, and here you see a bunch of people. So I don't want to go one by one, because even last 2 years result, there is a bunch of experts working on this case. So because I want to do this more dynamic, right? This is a fluid mechanics. So I prefer to, instead of going one by showing you the different contribution of authors, I would like to compare with a two fluid equation. Okay, now I'm going to consider the same problem, the same Muskat problem. But in the case in which I have two fluids. I have a fluid on top, and I have another fluid below. And this is given by this equation over here, which is somehow close. One can deduce this equation more or less similarly, and you have kind of some equal difficulties because it's not local, not linear, etc. But for example, this equation is more explicit. But what I want to do for you is to compare the situation in which we have two different fluids, and in the case in which we have one fluid, okay? One reagent and one fluid, okay? So to summarize all that result, I want to use this table that you see over here. And then I'm going to compare the one fluid case with the two fluid case. So remember that at the linear level, we have a parabolic setting, right? With the square root of the Laplacian. So if you consider any subcritical case, what do I mean by subcritical? There is a scale invariant situation, okay? Scale invariance for the equation. So if we reparameterize the profile, the function that gives us the profile in this way, okay? So if we move lambda, our solution remains to be a solution for Muskat, okay? So if we have the stable situation in which we have the fluid below, or in the case of two fluids, we have here downstairs the denser fluid. So here we have two different densities for the case of two fluids. So we have density rho 1, here density rho 2. So if rho 2 is greater than rho 1, this is an unstable situation. Okay, we have this parabolic setting, and then we can consider solutions. So there is existing a uniqueness or local solution, local in-time solution in the subcritical setting. So they are resolved using different subcritical spaces, but the point is that there is always the problem is well posed, local in-time. Okay. If you consider a small initial data, okay, if you consider a small initial data, then in the critical setting there is globalization. So in this case, essentially the parabolic behavior is stronger than the, let's say, the non-local behavior, and then we have global system solution for all time. One important thing is just that we have like different behaviors in the case of one fluid and two fluids. For example, in the case of one fluid, it is not possible to have churning. Okay, so what do we mean about churning? For us, turning is just that because gravity is pointing down, If we start with a graph, okay, turning is when in finite time we have not a graph anymore. We don't have a graph anymore. So this is turning. Okay. This is turning. We start with a graph initially, and then in finite time there is no turn. I mean, the solution is not a graph anymore. So in the case in which we have one fluid, there is no turning, but in the case in which we have two fluids, it is possible to have turning. Okay. For example, in the case of one fluid, okay, it is possible to have finite time singularities that we call a splash. Okay, a splash situation is when, let's say, two different particles collide in finite. Okay, this violates the incompressibility because of the incompressibility. Let's say that we have one label for each particle, right? So in finite time, two particles which are completely different collide, okay, and became one particle. So in the one fluid case, it is possible to have singularities, like splash singularity. By splash, we call this a splash because in the point of collision, I mean, the regularity of the interface remains. So you suppose that you have like a smooth interface. This thing is evolving in time. And then in the term of the collision, when the two particles collide, the regularity of the interface remains. Okay. But for example, in the case of two fluids, it is not possible to have this kind of thing. Okay, recently there have been results proving local existence and uniqueness, well-posedness, local in time in the critical setting for the case of two fluids. Okay, but there is no global in-time solution. So it is possible to have, in the case of two fluids, formation of singularity. Okay. So in the case of one fluid, in the case of two fluids, it is possible to have turning. Okay. So once the solution turns, there is a setting when there is formation of singularity. Okay. So it is possible to have the one. So what I want to do for you after this very quick summarize of results, what I want to show you, I want to solve these two questions that we are able to have a local system in a critical setting, okay, for the case of one fluid, and also we have that the solutions are global. So I'm going to answer to these two questions positively, okay, for the case of one fluid, okay, and then close this kind of table in which you can see like a kind of overview of results for these problems. Good. This is the result together with Hong Jidong and Hui Quan and Hui Nguyen, in which we prove that if you remember the scaling, Lipschitz profile are critical. Okay? So if we start with an initial data, which is Lipschitz, we have a solution for all time. We call this solution classical because our derivative in time is well defined. It's a function in L2, okay, for almost every time. And then we propagate the regularity, okay? So it's a global system result that converges properly to the initial data and satisfies the counter equation that they showed you at the very beginning, okay? Good. And very important thing is that this solution is unique. Okay. Okay. So the way we got this solution is with a regularization that make a limit to be a viscosity solution. By a viscosity solution, I'm talking about Crandall-Rabinovich, Crandall-Lyon viscosity solution definition. Okay. I'm going to explain this in a little, but if you think by this we mean viscosity solution in the sense of let's say Hamilton-Jacobi equation. Okay, very good. So we have we find some solution, and this solution that we find are critical. That is for all time, and then they are unique. Okay, so this is a well-posted result, and this is the first construction of a unique global Stokes solution for the Muskat problem for initial data of arbitrary size. Okay, the important thing here is just that our initial data is not small. Okay, so the Lipschitz norm is as big as this. Okay, and the Lipschitz norm is critical. Okay, very good. Okay, so the point, let me show you the difficulties. I think I don't have too much time to give you details. So let me show you the difficulties, and then just I'm gonna try to explain you how we got the result. Okay, so the point is just that we are in a critical setting. Okay, we are in a low regular setting. So for example, for high regular initial data, it is easy to get the maximum principle for the Lipschitz norm. It is easy to satisfy the contour equation. Okay, it is easy to get uniqueness because we have a lot of regularity, but it's very difficult to propagate regularity. For example, this is an open problem. Okay, so we have a parabolic setting in which parabolic problem in which we are not able to propagate regularity. So let's say that you have 3 derivatives in L infinity, or 3 derivatives in or whatever space you prefer. We are not able to propagate regularity. It's an open problem. Okay. Okay, for low regularity, for us, it's difficult to get the maximum principle. It's difficult to satisfy the contour equation. And it's difficult to get uniqueness. But even though we are able to do that, okay, and then global well possible. Okay, this is like the main things that I have to show you. Very good. So what about the system? So suppose that you have 2 solutions, okay, which are Lipschitz, 2 solutions which are Lipschitz, and then we have at one point C11 regularity. What I mean by C11 regularity? What I mean by C11 regularity is just that we can put 2 parabolas, okay, and there our function have to pass between these 2 parabolas at the point x0. Okay, this is what we mean by C11 regularity. And if we have an order, okay, then the Hopf lemma gives us an order for the evolution. Okay, remember that this is the Dirichlet to Newman map, or the normal, the gradient in the normal direction for the potential gives us the evolution, right? So we have an order. So because this order, we are able to have a comparison principle for regular solution. Okay, we don't have the regularity, but with a very kind of a standard contradiction argument, if our solutions are regular, then we have an order. If we have 2 solutions initially at time 0 with an order, this order is preserved. Okay. Okay. So the proof of this is just the Hopf lemma. Okay. This is Hopf lemma. Okay. And this is a contradiction argument. Okay. The order follows using this order that gives the Hopf lemma, and then you can find a contradiction argument. Okay, so if we have this order for F1 and F2, then for these 2 solutions, we can consider Y as a parameter, and then we are going to have an order, okay, for the solution. Fx plus Yt is going to be less than or equal to Fx plus L absolute value of Y. And this is exactly what is given to us the maximum principle for the Lipschitz norm. Okay. Good. Then what? We have a maximum principle, but still we have this maximum principle for regular solutions. So what we do is to regularize the equation so that we remain having for the regularized systems the maximum principle. And well, let's suppose that K is the heat equation or whatever kernel that allows you to regularize the initial data, okay? So we regularize the system, and then what we have to do is to find global system for this solution, which is not easy. We have to use like new inequalities for the Dirichlet to Newman map. This inequality was known, but what we have to do is just the dependence, okay, of the Lipschitz norm. We are in the critical setting because Lipschitz is the critical regularity to have well-defined Dirichlet to Newman map and this bound for the potential or for theta in our equation, in our non-local crazy equation. But then with this inequality, we are able to prove global system, okay, with this regularization. Oh, sorry, with this regularization over here, okay. Good. Then we have to look at the nonlinear part, and we have two parts. This is the one that appears in the equation for theta. This is in the equation for theta. And this is in the evolution equation for FT. And the point is that we have a derivative, both are given by derivative things, okay, and because of that, we can integrate by parts, and we can pass to the limit. Here and here, we can pass to the limit as epsilon goes to 0, and at the end, we have the system. Okay. Diego, how much time do I have?
10 minutes.
10 minutes?
Yes.
Oh, good, excellent, thank you.
Okay.
Very good. So now we have the system part. And one important thing for us was to get uniqueness. And for that, we use viscosity solutions definition, right? So the viscosity solution definition that we use is a la Randall-Lyon, right? So we are going to put, forget about this technicality of semi-continuous. Let's think that F is continuous. So we have a test, a function C, which is a test, which is regular. We have a lot of regularity. Okay, for the test, if we have F minus C having a maximum, then we have is just that we satisfy this inequality for the test. Okay, this is another way to define weak solution. Okay, if we have amendment, then we have the reverse inequality. And a viscosity solution, and we have both a sub-solution and a super solution. Okay, we have sub-solution for this inequality, super solution for the other inequality. Okay. Okay, this is this is a new definition we're going to use. And the point is just that using the theory, this is something that is kind of tricky to prove, but we are able to prove consistency. Like we have a sub or a super solution with critical regularity and with this extra thing at one point. Okay, this extra regularity at one point. Then not only for the test, but also for the viscosity solution, we have the inequality. Okay. In order to prove that, we need to show some properties of harmonic solution that we didn't have, but I don't want to get into detail. Please forget about this because I'm running out of time. So at the end, for this critical solution, we are able to prove the comparison principle. Okay, so if we have an order, initially, then the order remains for all time. And then with that is what we prove unique, right? Because if the two solutions are the same, I can put F0 from above and from below. And then here I get at the end that F and G has to be the same. Okay, this is the way we get unique. Okay, so this is the result that we did in 2D when we have a graph in 2D. Well, now we are working in the 3D case in which we are finding more difficulties. I don't want to summarize the difficulty. I can show you 4. Technically, they are more, but we think that we can make it, and then we are writing that, writing this result right now. we see that we can have it simple. Okay. So I think I have around 5 minutes or a little bit more. In these 5 minutes, I would like to talk about the other result, which are Stokes waves, Stokes gravity waves. Okay. So in this setting, I want to use essentially the same equation and then replace Darcy's law, in which we have forces equal to momentum, by the Stokes law. Okay, in which we have forces equal to minus Laplacian of u. Okay, this is like Navier-Stokes, but I'm getting rid of the acceleration, right? So this is an approximation. Let's say that I'm averaging the velocity with the Laplacian, okay? If we think in that situation. Okay, so what I'm gonna do, so again, I'm getting rid of some constant to simplify its position. So viscosity is equal to 1 and gravity is equal to 1 to simplify things. And then the problem I want to talk about is in which we have two fluids of different density. Okay, so we have a jump of density, constant densities, function in complementary domains. Okay, and then this is moving by gravity, and I want to understand the line. Okay, here the velocity is more regular than the density. Remember that in Darcy, for Darcy's law, so velocity is at the level of the density. So here we have more regularity, right? Because we can invert the Laplacian. We can invert the Laplacian here. Okay, so the velocity is twice regular than the density. Okay, the velocity is twice regular than the density. So global system is not a big deal here, but we want to get the global dynamic. Okay, we can get also the interface equation. I'm going to skip this. There is a question or something. No. Okay, so I'm going to escape this. So let me just tell you that to do that, we use the Stokes. Okay, the Stokes is just the kernel that works when one uses Stokes law. So essentially, the contour equation is given by this thing in terms of this contour dynamic thing. This is gravity. This second component of the this C is the interface between the fluids, the different density fluids. Okay, this C2 is due to gravity, and this kernel over here is just this. I'm considering also the periodic setting, so that's the reason why we have over here hyperbolic cosine and hyperbolic sine, but essentially this is the Stokes law. Okay, if you see in this equation over here, okay, this part of the kernel over here, this is kind of similar to the vortex patch problem, but there is this component because of gravity. Okay, good. Let me show you the linear equation, and then I'm gonna end with the result. I don't have time to show you the proof, the schedule of the proof, but now what we have is the square of the Laplacian, but integrating minus the square root of the Laplacian. Okay, if we linearize as we did for the other case, what we have is that the evolution is given by this operator that is minus the square root of the Laplacian. So we can go also to the Fourier size and then get the solution given by by this operator. Now K, if K is big, this is well defined, it doesn't matter the sign, but we have this exponential over here, okay? So what we get is also a stable situation when the denser fluid is below, and a stable situation when the denser fluid is on top, okay? Our system is not ill-posed, it's gonna be well-posed, but we want to understand this stable and unstable situation. And this is exactly what we did at the nonlinear level, okay? So here you have previous result. If you're interested, we can talk when I'm done. I don't want to go one by one, but essentially what is most studying is when you have capillarity instead of gravity driven. And when it's gravity driven, you have global system result, but what we wanted to understand is the long-time dynamics. Okay, very good. So essentially what we can prove is stability in the unstable case. Okay, so we can prove this is a joint work with Rafa Granero and Elena Salguero. So essentially, if we have an initial data which is small enough, it's going to be given by a graph. Okay, we are going to use a graph. So our fluid, our interface is given by a graph. We have the denser fluid downstairs. So if our initial graph is small enough, then we have global system for all time. Okay, we also can show the decay, how decay the norm of the solution. Okay. As I told you, I don't have time. Okay, if we compare with Muskat, this is not parabolic. Okay, if you see at the linear level, this is not parabolic, and this is one difficulty, but we can manage because what we find is a very weak damping that help us to get the global system result. Okay, so with this weak damping, we have to deal with this weak damping and then get the solution. And then another thing that we can prove is exponential growth, okay, in the unstable situation. For that, we use some analytic spaces. I don't want to give detail because I'm running out of time. So essentially, this is the result that we can prove. If you give me a time, it doesn't matter how big, okay, as big as you wish, I can find a family of smooth initial data, very, very smooth initial data. And then for this very, very, very smooth initial data, I'm able to prove a system up to that time. And what is important for us is just that the solution grows exponentially in time. So this is what we call unstable, right? So the nonlinear setting, we can control this nonlinearity and then find exponential. Okay. Okay, thank you very much for your attention. I think I'm gonna stop here. Oh, and thank you.
Okay, thank you very much for this very nice talk, Paco. So now we open the turn for questions or comments. So if anyone has some question or comment, please raise your hand or open your microphone or type your question in the chat as we wish. Let's see. Paco, I have some curiosities.
Yeah.
You mentioned that in some reference that Antosev, he proved some result for bounded domain, no?
Who?
Antosev. In the, I think that the 5 slides before, when you showed the reference for the Stokes.
Yeah.
Which kind of yes, yes.
Yeah. When you have the kind of result they prove, like if the bounded domain has an irregularity, then you can have, let's say, global system for the solution. Okay. The point is just that usually there they use.
global existence with small initial data, or
No. For large data, but a la Judovich, like for the vortex patch problem. Okay, so if you start with a patch or with a jump of density, and then the regularity is enough initially, then you can have global system for this setting. Or maybe even not a patch. You have your density, which is in L1 and in L infinity, and then your solution exists for all time. It's like a type result similar to the Judovich solution for 2D Euler. Here you can consider 2D or 3D. And let's say that because of the constitutive law, so the velocity is regular enough to solve. You can have here the last canonical vector. So this is like 0, 1 in one dimension, or 0, 0, 1 in three dimension, right? And then your Laplacian regularize enough the density, and then because you have maximum principle, or if you start like in L infinity and L1, it is possible to have less than L infinity L1, maybe L3, or it depends on the dimension, the scale, and so on. But essentially, in the case we are interested in, having a patch, so you can have like L infinity, for example, having a patch. Then you have solution for all time. So what we wanted to do in our approach is just to say what the solution do at when the time is very large, and then we have this stabilization, and then this unstable situation with exponential growth.
Okay. Another question is that in your result you have a decay, right?
Yep.
Polynomial decay.
Yep.
Is that optimal?
I don't know. This is what we can do, but I don't know if it is optimal. What we realize is just because of this damping, the decay that we get depends on depends on the regularity of the initial data. So, for example, if you want to get more decay, you just have to put a more regular initial data. Okay, if you want to get more decay. It is optimal in the sense that it's the same decay that we get at the linear level. But if someone finds a better decay at the linear level, maybe it is possible to improve the decay.
Okay.
Okay.
Okay. Okay. Very interesting. Is there any other question or comment? Okay, if not, let us thanks again, Professor Paco. So thank you
very much.
Very nice talk. So I give the word to Juan to close the session.
Thank you, Diego. Thank you a lot, Professor Francisco Gancedo, por su amazing talk.